So hello and welcome to our channel again. So in this particular video we are going to derive the ground state energy for the harmonic oscillator. So we have seen and we have derived the different types of the ground state energy for different potentials, like the Dirac potential, for the infinite square wave, for the finite square wave. So what is that? To find out the ground state energy, we have to solve the Schrodinger wave equation. But in quantum mechanics, there is another tool, which is the variation principle, which we can use to find out the lowest energy or the ground state energy for our different types of the potentials, which I'm going to use in this particular video to find out the harmonic oscillator lowest energy or the ground state energy. So ground state energy of the harmonic oscillator we are going to find out in this particular video without solving the Schrodinger wave equation, without solving those complex differential equations. So let's start. First of all, we have to find out we have to assume our trial wave function, and our trial wave function is going to be a e to the power minus bx square. So this is our trial wave function on which we are going to use the different types of these things, and this is obviously a Gaussian wave function. This is a Gaussian wave function. So first of all, we have to calculate this particular normalization constant. So let's start. So to calculate the normalization constant, you have to do the integration from negative infinity to the positive infinity of psi x square dx is equals to the 1. Now integrating it for the a e to the power minus bx square into dx is equals to the 1. It means if we do this calculation, it will be a square integration e to the power minus 2b x square dx from negative infinity to the positive infinity equals to 1. So this is a Gaussian integral, and the solution of this particular Gaussian integral, is a square, and its solution is root under pi by 2b, and it is equals to 1. It means after further doing the calculation, a is equals to 2b by pi 1 by 4. So this is what your value of a is, and this is your normalization constant. Now what we have to do is to derive out the expectation value of kinetic energy and the expectation value of the potential energy. So to calculate the first of all we are going to calculate the expectation value for the kinetic energy, and it is equals to the integration from negative infinity to positive infinity of psi as a complex conjugate into minus h bar square by 2m d square divided by dx square psi dx. So now let's do our further calculations. So this is equals to the integration of negative infinity to positive infinity of a e to the power minus bx square into minus h bar square by 2m d square divided by dx square a e to the power minus bx square into dx. Now we are going to take out the constants, so it is equals to the minus h bar square by 2m, here a square, integration of e to the power minus bx square, and here the double derivative of your wave function, which is e to the power minus bx square dx. So this is again a Gaussian integral if you solve it, and if you will solve it, you are going to find out that this is equals to the minus h bar square by 2m b. So this is what your value of the expectation value of your kinetic energy is going to be. So if you want hint to solve this particular integral, it's quite easy. You can see the Griffith's last page on which it is discussed about the Gaussian integrals and their solutions. By seeing this, you can easily solve this particular integral. Now let's move on and do this same for the potential energy. So expectation value of potential energy is equals to the integration from negative infinity to positive infinity of your wave function, which is a minus bx square, and your potential energy operator, which is 1 by half m omega, 1 minute, which is 1 by half m omega square x into a e to the power minus bx square dx. Now again, if I will take out all of this particular constants, it will be a square half m omega square integration of e to the power minus bx square into x into e to the power minus bx square into dx. Now it is equals to the a square by 2 a square by 2 1 minute. This is our potential energy expectation value, which is 1 by half into k, which is m omega square. Okay, so here it will be x square. Sorry, there will be x square. There will be x square. Sorry for this. This is what I was thinking, that there should be x square. Okay, so now a square by 2 m omega square integration of this particular stuff, which is x square e to the power minus bx square. It should be 2b. 1 minute, let me write it. That here it should be minus 2b x square dx. Now this is again an Gaussian integral from negative infinity to the positive infinity, and this solution I'm going to write out as the expectation value of this particular thing is going to be a squared by 2 m omega square, and this solution is 1 by 4b root under pi by 2b. So this is a solution of this particular integral. Now moving to the next, a squared by 2 m omega square. First of all, I have to write down the value of the normalization constant here. It will be a square will be 2b by pi root under, okay, into m omega square by 2 into root under pi by 2b into 1 by 4b. Okay, now you can see this and this will cut out, and the expression is m omega square by 8b. So this is what the expression for the expectation value of your potential expectation value of potential energy. Okay, now the Hamiltonian, which is the total energy, is equals to the expectation value of the total energy is equals to the expectation value of kinetic energy plus the expectation value of your potential energy, which I'm going to write is the expectation value of kinetic energy was, the expression was h bar square by 2m, okay, and it will equal to b plus m omega square by 8b. Now I have to make the ground state. Okay, so for ground state I have to minimize this particular Hamiltonian, and for the basic rule of the differentiation, to minimize this I have to differentiate it with the parameter that I have assumed for my trial wave function b, which is the differentiation of dh with respect to the db, and this is going to be h bar square by 2m, and the differentiation of 1 by b will be minus m omega square by 8b square. So this is what the differentiation of this particular 1 by b will be, and I have to put down the differentiation of our Hamiltonian expectation value with respect to the b as 0. So we have to put this stuff as 0. What will happen is that it will be h bar square by 2m minus m omega square by 8b square, and equated it with 0. Now this calculation is easy. H bar square by 2m is equals to m omega square by 8b square. Now if I will do all of this sort of calculation, this 4 will cut out, and b square will be equal to m square omega square divided by h bar square, and here it will be 2. Now the value of b for our minimizing the Hamiltonian is coming out to be m omega divided by h bar, sorry, here it will be 4, and so here will be 2. So this is the value of b coming out to be for minimizing our Hamiltonian. So now I am going to put down this particular value of b in our equation of the Hamiltonian, which was this is equals to the h bar square by 2m, putting this as m omega by 2h bar, and here as plus m omega. What was the expectation value of the potential? Let me see. The expectation value of potential was m omega square by 8b. Okay, so m omega square divided by 8 into b, which will be m omega, and here in it will be 2h bar. So now let's do the calculation. So the expectation value of Hamiltonian for the minimizing this Hamiltonian is going to be this m and m will cut out, this will be cut, and this will be h bar divided by 2 omega. Okay, this is the expression, sorry, it will be here, it will be 4, sorry, 4, okay, and plus again it will be m and m will cut out, it should be omega square, sorry, omega and omega will cut out, it will be h bar omega by 4. Now let's add this, and you will get your ground state energy. Let me write it as ground state energy as 1 by half h bar omega, and this is the same expression that we got when we were solving to the Schrodinger wave equation. This shows that how I easily derive the lowest ground state energy while using the variation principle in a very easy way. So it was a bit mathematical, but not as much hard for the solving these whole Schrodinger wave equations and differential equations, applying the ladder operators and etc, etc. So that's why this is very easy method. Now what I'm going to do is that I'm giving you as to prove this particular results, which is the lowest ground state energy for the different types of potentials, like the infinite square wave and for the delta potential. This is your, let's say, assignment I'm giving you to do this. So this is the today's video. Thank you for watching my video.